So what I'd like to do this evening is tell you, like I said, about my research work at the Large Hadron Collider, the world's largest, most energetic particle accelerator, which is at the CERN laboratory near Geneva, Switzerland. So I wanted to start with a little bit of background about some physics that we should all keep in mind. So we have today our best theory of what the fundamental building blocks of the universe are and how they interact with one another. That's something which we call the standard model of particle physics. It's been around with us for a long time, since it was developed in the 60s and 70s. And we want to look at just a few of the basic things that it tells us, and then spend more time talking about the things it doesn't tell us, of course, things which we still would like to learn. So this is a poster about sort of the main elements of the standard model. There's actually a copy on the wall at the back. It's in many physics lecture halls around the world. And it tells us what are the fundamental constituents of the universe, and what are the rules and interactions with which they interact with each other that gives rise to the physical phenomena which we observe. Now, physicists are fond of saying that any theory which is really worth something should be simple enough to be written on a t-shirt. And I think you can agree, even this poster at this huge size, you can't probably read, certainly not from the back. So you might worry that maybe this model, our best model, is not such a good model, fails the t-shirt test. But of course, all of this is written in pictures and words and language. This is not the way that physicists express nature, express the laws of physics. And so in fact, the way we express the standard model is shown here. So this is the so-called Lagrangian of the standard model. If you go on to graduate school in physics, you take a course where you learn what each of these terms are. And I can tell you that this equation is the standard model. So all of the phenomenology, everything which we know, is embodied in this equation. Okay, so indeed the standard model does pass the t-shirt test. And as a hint of what's to come, I'll say that these bottom two lines, so fully half of this t-shirt, is filled with this symbol. There's a Greek letter called phi, and that is the Higgs. And you may have heard, until very recently, we didn't know that thing existed, and there was a big hole in our understanding of whether this standard model was correct. As I said, it's fully half of the t-shirt, so we certainly should try and answer that question. So what are some of the things that it tells us, the standard model? Well, it tells us that the fundamental constituents of matter come in two types. Three so-called generations. They live here 1, 2, and 3. There's the things we call quarks, which we've known about since the 60s. So these are the things which make up protons and neutrons, the things which you remember from high school chemistry make up the atomic nucleus. So with so-called up quarks and down quarks, this first generation of quarks, we can make a proton, for example, by combining two up quarks with a down quark, or we can make a neutron by combining an up quark with two down quarks. And this similarity explains a lot about why protons and neutrons are very similar to one another, behave very similarly. And then the other generations are like heavier copies of those lighter generations that normal matter is made of, which we can produce in accelerators, and then they very quickly decay. So what's very quickly? Well, the top quark, which we discovered only a little more than 10 years ago at Fermi Lab, just outside Chicago, decays in about 10 to the minus 24 seconds. So it has a very fleeting existence, decays to these lighter ones. However, it actually has an important role to play. The other types of particles are called leptons. The most famous example is the electron, so the thing which goes around the nucleus and the atom. The electron has a neutrino partner, the sort of thing which Mike was talking about in his experiments. And then again, we have these heavier copies in these heavier generations, so that a heavier cousin of the electron, this one is called a muon, weighs about 200 times as much as an electron, and will decay to an electron, actually neutrinos, in about 2 microseconds, or 2 millionths of a second. So those are the fundamental particles. Everything in the universe is made of this stuff. And in addition to these particles that we show, for each one there's an antiparticle, which is very similar, but has opposite electric charge, so antimatter, as it's called. And then these particles interact with one another in a limited number of ways, via 4 types of forces. And those forces are mediated by exchanging other types of particles. That's what's shown here in the purple. These are the so-called force carrier bosons, or particles. So for example, the first one, the photon, was introduced by Einstein theoretically in 1905 to explain what was called the photoelectric effect. He won a Nobel Prize for that. That's the particle that mediates electromagnetism, so electric and magnetic forces. That's the particle of light. That's what's coming out of these lights that we see. Then there are gluons, as they're called, which glue the nucleus together, that mediate the strong force. And then there are heavy particles called the W and Z boson, which mediate the weak force. So we'll talk a little bit more about the forces in a moment, but first let's just set the scale by looking at some sizes. So we have a cartoon here of an atom.